Ho ho ho! And welcome to the second part of this algorithmic modeling challenge video, where we are modeling Sierpinski stars or Sierpinski trees. Okay. In the first part of this block, I explain what a Sierpinski subdivision algorithm is, and then I explain the basic overall idea of how we're going to implement the algorithm. In this second video, I would like to show you that implementation by using Vanilla Grasshopper, which is a visual programming environment that is attached to a 3D modeling environment called Rhino. Okay. What's going to be interesting is that it's going to be super simple to do. It's a very simple algorithm. It's going to involve a little bit of data manipulation, which is always interesting to learn and good thing to learn. But you will see very soon that we will hit one of the limitations of Grasshopper, which is that we cannot really perform recursion. So in order to do this nested subdivision algorithm, we will just basically have to manually copy paste the block that generates the subdivision as many times as levels we want to subdivide. All right, it's part of the limitation of how vanilla Grasshopper without plugins and without any additions work. In the next video, I will explain how to perform that recursion in a programmatic way, being able to control how many levels by implementing the same thing using C# scripting inside of Grasshopper. Okay, and all right, less talking and more doing. Let's get ready and let's get hands-on. Great. Let's get started. So the first thing we're going to do is we're going to draw a triangle in Rhino. So I'm going to hit polygon. Number of sides is going to be equal to 3. And then I'm going to hit 0 so that I'm centered in the origin. And I'm going to just draw it here, for example. I'm going to press F7 to remove the grid, which I don't need. I'm going to create a curve parameter here in Grasshopper, set one curve, and I'm going to bring in this curve from Rhino into Grasshopper so that I can work with it. I'm going to drop a panel because I like having panels so that I can see what's going on in the wires. And then I'm just going to drop in here the bifocals plugin so that those of you who are not icon people, I'm sorry, everyone has mistakes. Just joking. But those of you who are not icon people, you can at least see what these components are. Okay. And so the first thing that we're going to do is, well, as per the algorithm that we were describing before, the first thing that we need to do is we need to extract the vertices from this polyline, okay? And then the second thing that we need to do is we need to figure out what are the midpoints for each one of those segments of the polyline. And then after we do that, we will start cherry picking which ones we need in order to join them with polylines. Okay, so how can we do that? Well, for example, in order to extract the points in of this polyline, there's two things we can do. We can either take the control points, and therefore what we will end up is with a list of the 4 points. So that's one way to go. Another way to go is to explode the curve into individual segments so that what we end up with is with 3 line-like curves. And then for each one of them, we can just get the endpoints. All right. And the endpoints will give me a list of the 3 starting points and the 3 of ending point. Okay. I think this is probably what I want to do because I will also want to use the individual segments. So I will want to use the line-like curves to find the point at the center of those segments. So by the point at the center of those segments, I'm going to find by evaluating the curve. So I'm going to evaluate the curve at the center. So that's going to be each one of these curves. And I'm going to drop here a panel that says 0.5 because I want to find the point that is at the center. Now, remember that evaluate curve takes a parameter. And for lines, the parameter is a value that goes through the domain of the curve, which for straight lines is always going to be from 0 to 1. However, because with these lines in the polyline come from an explosion, they're not exactly lines, they're line-like curves, but they're still curves. And their domain can be whatever. So actually, if I query this, you can see the domain of these lines is from 0 to 25, whatever. So if I reparameterize, I turn it from 0 to 1. So this is what I want here. So I'm going to reparameterize at the input. And then I'm going to, so that I get the points at the center of those lines. So if I do that, now I get these points, a list of 3 points, and I can kind of start working with this already. So for example, what I wanted to do, if you remember, is, for example, for any given triangle, what I wanted to do was I wanted to say, let me find a polyline, let me create a polyline that joins this first point with the next middle point, with the previous middle point, and with the same point again. So what I need to do is, I need to create a polyline that joins 4 points that are ordered in that sequence. So in Grasshopper terms, what I will need to do is I will need to create a list of points that are those 4 points that I have there in that sequence, in that exact sequence. So what I will need to do is I will need to do a little bit of list management so that I'm able to create a list of 4 points that has those exact 4 points one after the other. How am I going to do that? Well, you can see that here I have the 3 starting points, so 0, 1, and 2. But I have them on the same list. So the first thing that I'm going to do is I'm going to graft this tree so that I have each one of those points in a different list. And therefore, to that list, I can start adding other points, such as, for example, the point here, the points that are in the middle, right? So for example, let me say that I'm going to merge this tree that I have here. I'm going to merge it with what's coming from the second one, all right? You can see that it doesn't work because the structure of what I had before, the structure of what's coming from this component is 3 branches, 0, 1, 2, whereas the structure of what's coming here is one single branch called 0, 0. So what I need to do is just basically go ahead and also graft this this list, so that it takes the same shape and the same structure as the first one. You see these two. And now when I merge this one with this one, then this point is going to go here just because it has the same branch. This point is going to go to this branch because they have the same branch, etc., etc. So you see, when I merge them together, points that are on the same branch, they get merged together into the same branch. So now it's very nice because we have 3 lists that we could use to create polylines with 2 points each one. So actually, let me try to start doing that. So I'm going to create a polyline with each one of the 3 lists. And you can see that I have a polyline that starts from this one to this one, another one that goes from this one to this one, another one that goes from this one to this one, and we have the first side of each one of the 3 triangles, which means we are on good track. Now, what is the next thing that I need to do? What I need to do is I need to say, well, the next thing that I should add here, the next point that I should add to each one of my 3 lists should be also a middle point, right? But it should be the one that is before each one of these, each one of the vertices. So if I was looking at vertex 1 and then I was adding the one after, then what I need to do is I need to add now the one right before. How is that going to work? Well, turns out I have a list of ordered middle. I have a list of 0.012. I have another list of midpoint 012, the ones right after. So if I now want to add here another list to be combined with this tree, but what I need is, instead of these points in the same order, what I need to do is I need to point to the middle points that were before. So basically what I need to do is I need to take this list and change the order of these points so that all of them shift 1 position to the back. And by doing that, I will be able then to plug that shifted list into here and then have the same points, the same middle points, but added to the list with 1 position less. This is very tricky to explain. Let me show you how that works. I'm going to take this evaluate curve and I'm going to shift that list. All right? Shifting takes the whole list and moves all the elements 1 position or several positions up or down. So I'm going to take this and I'm going to say, I want to shift. So right now I'm shifting 1 unit. And what is happening is you can see that the elements are moving 1 position to the back, right? So 0 minus 7 was position 1 and is now position 0. 6, 3 was position 2 and is now position 1, which I think is kind of what we wanted. And also you can see that the wrapping is true, which means that the element that was first, instead of going back to -1, getting lost, what it does is it goes back to the end of the list, which is also the behavior that we want. So now I can just graft this tree so that it gets the same structure that all of the other ones has, except for the fact that, look, the structure is not identical. This has 3 levels and this one has 4 levels because it comes from an additional processing of the data. So if I were to now merge this tree, the one with 4 levels, into this one that has 3 levels, they would not merge correctly because now I have a bunch of different trees, branches in the trees that have different depths. One way to solve this is by making sure that this branch has the same amount of levels as the previous ones. What I could do is I could offset everything to the left, but I think there's actually a simpler solution, which is, you see all these zeros that I have here leading? Those are redundant. That is not information that I really need. So something that I can do is for each one of the previous branches, I can just go ahead here and simplify the tree so that I remove branches that are redundant and don't really contain information. If I do that for this one, I get 0, 1, 2, much cleaner trees. If I simplify this one here, I get 0, 1, 2, much cleaner. So now everything is 0, 1, 2. And if I clean it here, you now can see simplify. This becomes 0, 1, 2. And now everything is merged correctly into the same branches. And you can see that each one of my polylines is great now because it joins the vertex, the next middle point, and the previous middle point. Right? How awesome is that? The last thing that I need to do is to just duplicate again the same original point so that I close up the triangle. So I can just do that by saying, well, the same starting point, I'm going to add it again to the last one. Oh, and this is not working. Why is this not working? All right, sorry, I made a mistake. This was not working because, look, even though it looked like, before I joined this, it looked like each one of the polylines, each one of the triangles was this one and this one. And then this one and this one, and this one and this one. But it turns out that when I bake it, all right, and I take, for example, this one, look, it's actually, the curve that I'm getting is actually this one instead of this one. And the other one is this one, and the other one is, yes. So it turns out that I was shifting the other way around. So I was shifting +1 instead of -1, which is what I should have done. So I'm going to shift the list in the opposite direction. So I think I now visually, I get the same thing, but if I were to bake this, and take them out and then ungroup them, so you would see that this is the right triangle, this is another right triangle, this is what I wanted to be getting. And then if I duplicate the last point now, you see that the triangles are now closed. And if I actually create a boundary surface around each one of these polylines, you can see that the triangle has already been done. Okay, so all right, so that's great. So what can we do? I'm going to clean up all these parameters. So yeah, it turns out that control points was not an interesting way to go. And check this out, how clean and how simple doing this subdivision has been with just a little bit of data tree manipulation. All right. Okay, let me save this so that it doesn't break, just like Sierpinski, so it doesn't break like in my previous video. So I'm going to group all of this. Okay, so this is the algorithm that takes one curve, okay, and then it takes one triangle or one polyline, and then it subdivides it into a bunch of triangles for that polyline. So what I'm going to do now is I'm going to try to apply recursion to this algorithm so that I'm going to try to subdivide each one of the triangles. The problem is that Grasshopper doesn't really let me perform recursion programmatically. Okay, I cannot create, because Grasshopper is a directed acyclic graph, which means that if I try to now plug the result of this back into the beginning so that I create a loop, you see everything breaks because I cannot connect the output of something into an input that will lead into the same output, creating a loop. All right, it's the part of how Grasshopper behaves. There are plugins that allow you to work around that limitation, but I'm not very interested in showing those at this point. I'm more interested in just the concept. The concept being, well, the way we would do this manually with simple Grasshopper, vanilla Grasshopper, is that we just simply take the whole thing, we copy paste it, and the output of the first subdivision, we just feed it into the input of the next subdivision. And then we get this family of triangles that conform the Sierpinski tree. And if we want 2 levels, we can do it. If we want a 3rd level of subdivision, we can subdivide even more and then plug this here. If we want another level of subdivision, we can just plug this in here, add another layer, etc., etc. Right? And then we end up with as many levels as we can basically manually copy paste. This is one of the limitations that Grasshopper, this procedural environment, has right now. Okay. In the next video, I will show how to write, using scripting, how to write this same logic, but then be able to apply this recursion programmatically. All right. Another thing that I would like to highlight before I move on to the next video is everything that we have done here. We've done it for this nice equilateral triangle, but honestly, there's nothing in this algorithm that requires that the polyline that we work with is a perfect triangle. It doesn't even require the polyline to be a triangle at all, because everything that we have done is working assuming that we just had an input polyline as a sequence of points. So if I were to, for example, just draw a rectangle and feed that in as a curve, you can see that the division algorithm just works exactly the same. It just creates triangles for each one of the angles of the polyline. If I were to create a free form sort of polyline and then use that, it would also work perfectly. I would have this Sierpinski subdivision of this polyline. And also, super nicely, this is also not bound to 2 dimensions. So I can just take this polyline and I can start now messing with the vertices and make this polyline volumetric, give it depth. And then very interestingly, I get also Sierpinski subdivisions for each one of these segments, each one of the angles of the polyline, which I think it's pretty cool. So I think with this, I'm happy with the Sierpinski subdivision algorithm that we have programmed in plain old Grasshopper. Okay, and I'm going to go back to the triangle because, you know, it's nice. It's the Christmas tree kind of feeling. All right. Now, if you're interested in knowing how to implement all this logic, but instead of using components, we write the code inside a scripting component, and how to implement programmatically with a slider without the need to copy paste this 17 times, how to implement this recursion subdivision, then make sure you check my next video. Okay. And if you like what you saw, hit a like, hit subscribe, etc., and all those things. All right. Thank you very much. See you in the next video.